Hi and welcome back to the Insight My Life channel. So today we're going to be going over question 322 from the Society of Actuaries published questions. So I advise you to take a moment, pause the video, and read through this question, and we are going to cover it right now. So the first thing I want to ask is, what is shared between the cars? Gas prices. It's the same thing that they're paying. Despite their mileage differences, they're still going to be paying a flat $3 per gallon in this example. So we don't want to exceed a total cost of $7. So that means that in order to do this, we're going to have to find what is the maximum amount of gallons of gas that we can use in order to stay below our $7 threshold. So in equation form, that's our $3 per gallon price times our total gallons less than $7. So if we solve this for total gallons, we get 2.333, or 2 1/3. So we're trying to keep our total gallons used under 2 1/3. So now that we have the price defined, let's go ahead and take a look at the mileage between the cars. So car 1 is normally distributed with the parameters, and it travels at 15 miles per gallon. And car 2 has the same parameters of the normal distribution, except that car 2 travels at 30 miles per gallon. So X and Y are defined in terms of miles, and we're going to redefine them in terms of gallons. And so we can actually do that by using our MPG that's given to us. So we're taking our amount of miles. So if X and Y represent the random variable for amount of miles, then we're taking that and dividing it by our miles per gallon in order to redefine this question. So what we're going to do now, in order to turn this in terms of miles, is we're going to actually multiply through by our denominators. So our least common denominator here would be 30. So if we multiply the entire equation by 30, we get 2x plus y less than 70, and that would be our equation in terms of miles. So you notice that I'm saying that by multiplying out our MPGs, we're actually redefining the equation in terms of miles. And this is important because our random variables are normally distributed in terms of miles. So we can't solve it unless we think of this in terms of miles. Okay, now what we're going to do is we're going to take our 2x plus y and redefine a new variable w equal to that 2x plus y. So now we want to get the parameters of this new variable. So w equals 2x plus y, and we're going to be finding the expected value of w. So you can see here we have the expected value of 2x plus y. So if we break that up, the expected value of 2x plus y, we can split it up as 2. Any constant in an expected value can just come out. So 2 times the expected value of x plus the expected value of y. We solve that, we get 75. Now for variance, it's a little bit different. Remember that when you take a constant out of a variance equation, you have to square the constant. So we get 2 squared times the variance of x plus the variance of y. And now remember, they didn't give us variance in the problem. They gave us standard deviation. So we have to square that to get the variance. So that's why you're seeing a 3 squared here. So when we do that, we get 45. Now we're trying to solve for our modified version of this equation where we're saying w, where w is equal to 2x plus y, is less than 70. So in order to do that, we're going to have to normalize our 70 value. So remember the z-score formula, x minus mu over the standard deviation. So mu represents the average. So it's 70 minus the average over the standard deviation gives us a negative 0.75 as our z-score. Now you can see I have the normal distribution table here, and we're going to be looking this up in the normal distribution table. Now, you'll notice right away that there are no negative values in your normal distribution table, at least not this normal distribution table. But that's okay, because in order to solve this, you actually just would take the complement of whatever's given here. Kind of think of the bell curve here. These values are all to the right of our halfway point on the bell curve. And so this normal distribution is taking everything to the left-hand side of that z-score. So in order to get everything, rather, if you're going to think of it as a negative value on the normal distribution chart, then you're actually taking the complement of this. So basically, you're just taking 1 minus whatever the positive version of this is in the table. So for example, we have 1 minus 0.7734. That's what we get when we look it up. And we get a final answer of 0.23.